Okay. So we look at backprop. Okay, backprop is a, I guess, name invented in the neural network community, but it's essentially chain rule. So that means we'll just revise calculus for the next few minutes. So so what's the chain rule? Okay, so here's a picture, I guess more inspired from neural network community. But so what's chain rule? So let's say you have a function h. Okay, actually let me go to the next slide and then come back here. Yeah. So let's say we have a function g. Okay, it has three arguments, a, b, and c, and in fact the function is very simple: a times b plus c. Okay, so such a function can be represented as what is called a computational graph. Okay, so this is a very simple computational graph. It's literally saying there are three inputs, a, b, and c. A and b is getting multiplied at a multiplication unit node, and then that output is being fed to an addition node where c is being added to it, and then that's the output g. Right? G is over here. Right? This is g, and that's a, b, and c. Intermediate output, we can call it something. I think I call it yeah, h. Let's say intermediate output is called h. Okay, h is equal to a times b. Okay, so backprop is nothing but using um, chain rule to compute what. So goal is to compute the partial derivative of g with respect to a, partial derivative of g with respect to b, and partial derivative of g with respect to c. Okay? These are the three things we want to compute. That's all. The gradient of the output with respect to its inputs. Okay, there are three inputs, so gradient of the output with respect. So three numbers. So this is what we want to compute, but we want to compute it. I mean, actually, by just looking at the function, you can compute, right? What is the gradient of g with respect to c? Right, one. And what's the gradient with respect to a? Yeah, b. And gradient of g with respect to b is a. That's everybody is completely comfortable with that, right? Okay. So so we can eyeball what the gradient should be. So we know what the answers are. Okay, what the of the top right thing. So we know what the gradient of g with respect to a, b, and c are. And so grade backdrop is as follows. So we start with the output g, and let's just write gradient of g with respect to itself is one. Okay, because if g is g is equal to g, so gradient of g with respect to itself is one. Okay, so what we'll do next is pass this, backward propagate this gradient information. And how are we going to do that? So let's focus on this addition node. Okay, just focus on this addition node. This addition is g is equal to h plus c. H was this intermediate computation, but let's ignore this intermediate computation for now. Let's just say h is my input now. Okay, that means g is equal to h plus c. What is the local gradient? Now I'm going to call it local gradient, local to this node. The gradient of g with respect to h, okay, is just one, right? Gradient of g with respect to h is one. Gradient of g with respect to c is one, right? So these are my local gradients. Gradients of g with respect to one of its input is one. Gradient of g with respect to its other input is also one. Okay. Now I'm going to backward propagate the gradient by an intermediate computation by doing the following. I'll take the local gradient, multiply it with the gradient at the output that I have gotten. Okay. At the beginning, I'll get this gradient, which is just one, and pass it back. Okay. So there's nothing interesting happening here. So since all these three are one, so one times one is one, that will be passed back, and one times one is one, that will be passed back. So gradient of g with respect to c is one. That we already saw. It's just the addition part. Okay. Now the passing back is going to be useful when we compute the gradient of g with respect to a and b. So far we have not done that. We only computed the gradient of g with respect to h. That was the local gradient with respect to the additive node, right? Now what we'll do is we'll compute the local gradient of h with respect to its inputs. Local gradient of h with respect to its input a is b. Local gradient of local gradient of h with respect to its input b is a. I mean h is equal to a times b, right? So that's it. That's the local gradients. Okay. So the all I said is this. Okay. Local gradient of h with respect to a is this. H with respect to b is this. Now we have these local gradients at this other node as well. So what we just need to do is observe that gradient of g with respect to gradient of a is gradient of g with respect to gradient of its input h. Okay, g has two inputs, right? This is g, has input c and h, right? Remember, uh, times times gradient of h with respect to its input a. Okay, so this is chain rule. Okay, g with respect to a is g with respect to some intermediate computation times intermediate computation with respect to a. And so you can just so backprop just means that this guy was computed. So if you do a forward computation, this guy uh, okay, so this guy was computed at this node, right? So at the node which is towards the end, that gradient is passed back, okay? Because when it's passed back, the previous node computes this local gradient, I mean this gradient h with respect to a, and then gets back this gradient from somebody downstream and multiplies them together and passes it back. So every node, what it does is compute some local gradients of its output with respect to its inputs, and then get some gradients from some downstream guys, okay, whatever gradient it is, and somehow the dimensionalities and everything match, okay. So you just do multiplication of these two gradients, local gradient and the incoming gradient, and pass it back to somebody upstream, essentially, or somebody who's closer to the input. That's all. Okay, that's mechanically that's what's happening, but essentially it's just chain rule like this. Okay, and so that was the picture here. You have some node h of a comma b for example two inputs. Okay, it could be some arbitrary computation, doesn't have to be multiplication or addition or anything. You get a local gradient. So let's say the final output is g, then somehow some upstream computations will send you eventually a gradient of the output with respect to that h. Okay, so this node's output, that thing multiplied by the gradient of the current node's output with respect to its input. Node's output is h, its input is a, so that's the local gradient. So this times this will give you the gradient of g with respect to a. So gradient of g with respect to a, is nothing but gradient of h with respect to a times gradient of g with respect to h. Okay, so whatever the incoming gradient, okay, this is some, for example, could be a vector times the local gradient. This could be vector. You multiply these two, then you'll get the gradient with respect to a. Okay, or it could be scalars and whatever. So, and we'll actually see that nuance right now, actually. But before that, let's do another little bit more involved example, which is this. Okay, now g is a function of four inputs: a, b, x and y. Okay, and the computation is a little bit messy, right? It's 1 by 1 plus e to the power minus ax plus by. So a little bit messy, but you can still draw a computation graph. Okay, what is happening? A is getting multiplied with x first, b is getting multiplied with y first, and then those two are getting added. So two multiplications and then some addition, and then it's and then I've written a huge blog saying whatever that this computation is, that's 1 by 1 plus e to the power minus that number. Okay, that's this node here. Okay, I could have further split this node into multiple subnodes, but for now I've just written it as 1 by 1 plus e to the power minus z. Okay, so this function is like the sigmoid function. Okay, it's called a sigmoid function, like an s function. But anyway, so in this example, what do we want to compute? We want to compute the gradient of g with respect to a, with respect to b, with respect to c, sorry, with respect to x, and with respect to y. Okay, and I've given you some nominal values a, b, x, and y. So at this current input, tell me the gradient of the output with respect to the current input. Okay, that's the question. And how do you do that? You can just eyeball. You don't have to draw this diagram. You can directly, not eyeball, but at least compute the gradients. Do chain rule and remember some properties, and you can do it. But here we'll do chain rule. Okay. For that, we just want to find. First thing we find is the gradient of the last node with respect to its input. So its input is one scalar number. Okay, single number. Its output is one single number. So gradient of g with respect to z is going to be some single number, and you will see that that evaluation is 1 by 1 plus. So if the function is 1 by 1 plus e to the power minus z, then the gradient of that function g with respect to its z, let's say g is equal to g of z is equal to that. Then this is equal to what is this? So e to the power minus z divided by 1 plus e to the power minus z the whole square. It's just a derivative of this of this function with respect to its input z. Is this clear, or is this a little bit confusing? Okay. So then you substitute z, whatever the value of z is. So what is the value of z? Uh, ax minus 6 plus 4, 2. Okay. Minus, or is it minus 2? Yeah, minus 2, and then you substitute all this, and then you'll get a, what is the local gradient? E square divided by 1 plus e square the whole square. Okay, this is the, so square only because z was actually equal to minus 2. So this formula, sorry, this formula here substituted here for z is equal to minus 2 gives you that number. Okay, that's the local gradient. Okay, now you got the local gradient. Now what is the gradient of z with respect to its inputs? Let's call its inputs c and d. Okay, gradient of z with respect to c is 1, gradient of z with respect to d is 1 because it's an addition operation. Okay, so local gradient of z with respect to its input is 1. So you have the incoming gradient, multiply with the local gradient, you pass it back. Okay, so the gradient that is going to be passed back to this node, multiplication node, and this multiplication node is just e square by 1 plus e square the whole square. Okay, so sorry, the numbers in the brackets are just the evaluation. Okay, a times x is minus 6 and b times y is 4. Those are the numbers in the brackets. And so and that's what I wrote here. So the local gradient of z is, since it's 1, that's 1 here, and the incoming gradient was this. So the gradient of g with respect to c over here is the product of local gradient times the incoming gradient, and similarly here is the same thing. Local gradient is 1, so gradient of g with respect to d is 1 times the incoming gradient. This part is fine. I'm just very elaborately writing everything. Um, and then now we have the gradients of g with respect to c. Now they are incoming to c and d, and we know what the gradients of c and d are with respect to their inputs. It's just the opposite argument, right? It's in the sense that gradient of c with respect to x is a, gradient of c with respect to a is x. Okay, so you can multiply those things appropriately. Okay, with the incoming gradient, and that will be the gradient of g with respect to a, x, b, and y. If you want, I can do it on paper if somebody wants it. If somebody is doubtful, ask me after the class. Yeah. Okay. So why are we looking at these examples? Because you will see that, I mean, we'll not really do backdrop by hand. I mean, we'll not compute these things by hand, but the systems are doing it. Okay. The packages, the Python packages that you're using actually do this. Okay. And the people are really inventing new and new techniques to do this automatically, even for very complex things like programs. Okay. If you write a computer program, you can actually differentiate the computer program with respect to its input. A generic program, like which has the if else statements and things like that. Okay, so these fall into this bucket of things called automatic differentiation techniques. Okay, which can be done for programs, which can be done for simple, in our case it's just simple functions and so on. And so although we may not be doing this, we won't code this. These are what the systems are doing, so we need to know this. That's all. So here's another example. So let's say the local node is h of a comma b, two inputs, and that h output is being in two different places, is being used in two different places, eventually to some final thing. Okay, so there may be two incoming local gradients. Okay, so two different branches of the downstream computation. Then what you do first is just add these two together. Okay, these two local gradients, so these two incoming gradients, add them together, and then multiply with the local gradient to get the gradient of final g with respect to a. Okay, all I'm saying is, let's say g is equal to g1 plus g2. Okay, that means that there are two gradient paths to come back to this node. Then you just add them together. So you add those gradients together, multiply with the local gradient, pass it back. Okay, and there's also dimensionality aspect. For example, let's say we saw that the gradient of a vector, so gradient of the output, let's say output is a loss function, and let's say my parameter is a vector, then the gradient of the loss with respect to the vector is going to be a vector, right? The gradient is always the same dimensionality as the input that drives that. So let's say my incoming gradient is a vector, okay, and my current computation h is a scalar, okay. This h is a scalar, and its inputs are a and b, which are also vectors. Okay, so let's say a is p cross one dimensional vector, and b is q cross one dimensional vector. Okay. Sorry, I think I said h is a scalar, but it's fine. H has to be the same dimension as the incoming gradient, by the way. Um, Sorry, the dimensionality of h, for example, h is the same dimension as the incoming gradient. So if the incoming gradient is 5 dimensions, then h has to be 5 dimensional, like 5 dimensional output. Okay. So what you do is take this gradient, the local gradient of h with respect to a. So if a is a vector, h is a vector, then the gradient of this vector function with respect to vector is going to be a matrix. Okay, it's called the Jacobian. I don't know how many of you remember some calculus, but it's called a Jacobian. Okay, so and it's going to be a matrix, and it's going to be P cross R. Okay, where what is P? P is the dimensionality of A, and R is the dimensionality of H. Okay, it's going to be R columns and P rows. And what you're going to do? How do you do this backprop in this situation? Is that the incoming gradient is actually a vector. You multiply this vector with this matrix. Okay, then you get a P cross 1 vector, and that's the right dimensionality to pass back because A is P cross 1. Okay, so A is P cross 1. So you had a R cross 1 vector multiply with the local gradient, which is a matrix, such that it comes back into P dimensional space, and then you pass it back. Okay, so that's the vector notation. So it'll take some time to internalize this, but it's essentially just chain rule, just being explained in a visual and geometric way. I mean, in terms of computational graphs. Okay. Um, let's not worry about these aspects now. Um, yeah, I think I'll skip that. So I think those three slides were just giving some minor points about how it looks like in a system. But we'll actually, since we anyway, we'll use PyTorch and maybe even TensorFlow. We'll see that later. Okay. So now what I'll do is uh, show you. I don't know if I'm still connected. I am not connected. Okay. So just give me 1 second.